Thank you everyone, and welcome to college algebra. This we will be discussing section 4.1 today, which talks about exponential functions. So, what is an exponential function? So, the exponential function, f, um, with base of b is defined by f of x equals to b power x, or y is equal to b power x. And the b is a positive constant, where b is a positive constant. It's a positive constant or number. It's a positive constant or number other than 1. Okay, so b is greater than 0 and also not equal to 1. So b can be any number greater than 0 and not equal to 1. B is not equal to 1. And x can be any real number. X can be any real number. So let's start off with graphing exponential functions. So in our first example, let's call this example 1. Example 1, the exponential function f of x equals to 40 equals to 42.2 times 1.5 power x. Models the average amount spent. This average amount spent f of x in dollars at a shopping mall after X hours. After X hours. What is the average? What is the average amount? Is average amount spent? Average amount spent to the nearest after 3 hours. Yes, after 3 hours at a shopping mall. All right, so we are told f of x is the amount spent after x hours. So f of x is equal to 42.2 times 1.56 for x. This is the amount spent after x hours. So after 3 hours, that means x is equal to 3. So f of 3 is 42.2 times 1.56 power 3. And this should be, if we evaluate this on a calculator, this should be approximately 160.2876. So this is approximately 160 hours. It is also approximately 160 $160, I should say. So the amount spent after 3 hours is about $160. Let's look at another example, example 2, where we try to graph an exponential function. Graph f of x is equal to 3 power x. All right, so let's pick some x coordinates and find the corresponding y coordinates. Then we get a pair of points that we graph. So x is -2, -1, 0, 1, and 2. And we have f of x is equal to 3 power x. Okay, so f of -2 is equal to 3 power -2, which is the same as 1 divided by 9. And f of -1 is equal to 3 power -1, which is the same as 1 divided by 3. And f of 0 is equal to 3 power 0 is equal to 1. F of 1 is equal to 3 power 1, which is 3. And f of 2 is equal to 3 squared, which is equal to 9. All right, so we have a pair of points for x and for y, so we cannot graph our function. All right, so let's graph our function. And this is, um, all right, let me draw this down here. and this is 0. This one, this is -1. -4. So this is -1, -2, -3, and -4. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say this is 10. All right, so the first pair of points are when x is -2, y is 1/9. So 1/9 is just below, just above 0, so -2, and with this point, we use a different color. So -2 and 1/9 will be about this point. -1 and 1/3 will also be slightly above this, will be about this point. 0 and 1 will be this point. 1 and 3. When x is 1, y is 3 will be about this point. When x is 2, y is 9 will be about this point. All right, so we have these pair of points now, so we can join them, and this should be the graph of. So this should be the graph of. This should be the graph of f of x is equal to 3x. All right. Let's look at some characteristics of an exponential function. Let's look at some characteristics of an exponential function. Okay, so characteristics of an exponential function. The domain of f of x, for any exponential function f of x, the domain consists of all real numbers. So from -infinity to positive infinity. But the range goes from 0 to positive infinity. The range of an exponential function goes from 0 to positive infinity because when when the value of x is 0, when the value of x is 0, you get a 1. When the value of x is negative, you get very small positive numbers. And when the value of x is a positive number, you get bigger and bigger positive numbers. So the domain is never in the negative. The domain is the range is never in the negative. The range is always from 0 to positive infinity. And so for the graphs of f of x is equal to b of x, if you remember from what we just drew, it always passes through the points 0, 1. Whenever x is 0, when x is 0, f of x is 1. So the function passes through 0, 1. Because whenever the x value is 0, you get b power 0, which gives you 1. So the y-intercept is 1, and there is no x-intercept. The graph doesn't cross the x-axis. And if b is greater than 1, then the graph goes up to the right. If b is greater than 1, the graph goes up to the right. And if the greater the value of b, the steeper the increase. And also, if b is between 0 to 1, then the graph goes down to the right. So you can see here the red graph, it goes down to the right because b is between 0 and 1. And the blue graph, it goes up to the right because b is greater than 1. So the blue graph is known as an increasing function. As x increases, y also increases. So it's an increasing function, whereas the red graph is a decreasing function. As x increases, the value of y decreases. So it goes down to the right. It's a decreasing function. And also, the exponential function uh, is a one-to-one function, and so it has an inverse. So by horizontal line test, you can see that if you draw a horizontal line through the graph, it will intersect it at one point. So it's a one-to-one function, and it also and that means it also has an inverse. And the graph of f of x, it approaches the x-axis, but it never touches the x-axis. So the value is never 0. The value of y is never 0, although it gets closer to 0, closer and closer, but it's never 0. So it gets closer and closer to 0. So it never touches the x-axis, although it gets close to it. So it has a horizontal asymptote. We say it has a horizontal asymptote because as it gets closer and closer to the y-axis, it never touches the y-axis. And also, when it comes to transformation of exponential functions, they are similar to its transformations are similar to the standard transformations that we've looked at in earlier chapters. For example, for a vertical shift, if g of x is equal to b of x, if we add c, that means f of s is shifted c units upward, and g of x is equal to b power x minus c. F of x is shifted c units downwards. And for the horizontal shift, also b exponent x plus c. If c is added to the exponent, then f of x is shifted to the left by c units. The c is always a number, whereas the x is the variable. And g of x is equal to b power x minus c, means f of x is shifted to the right by c units. And when it comes to reflection, g of x is equal to minus b power x. That reflects f of x about the x-axis. So g of x is equal to minus b power x, means the y values become negated. So for every given x, the y values are multiplied by negative, and so the y values become negated. So that reflects the graph about the x-axis. And whenever g of x is equal to b power negative x, that means we reflect f of x about the y-axis. So it means the x coordinates now become negative. So positive x coordinates now become negative x coordinates. So that is a reflection along about the y-axis. And the other transformations which involve vertical stretch or shrink, when g of x is equal to c, if you multiply the exponential function by c, where c is any number greater than 0. When c is greater than 1, then the graph is stretched. F of x is stretched by c units. And when c is between 0 to 1, then the graph shrinks by c units. And for the horizontal stretch or shrink, when g of x is equal to b power cx, it shrinks the graph of f of x. And if c is greater than 1, it stretches. If c is greater than 1, the graph is shrunk. And if c is between 0 and 1, the graph is stretched. Okay, so let's look at an example. Let's look at an example to go over one of these. All right, so let's look at an example. So this should be our example 3, and it says, use the graph, use the graph of f of x is equal to 3 power x to obtain f of x is equal to 3 power x minus 1. All right. So we have to use the graph of 3 power x to obtain the graph of 3x power negative 1. 3x power negative 1 is a shift to the right by 1 unit. So this is a shift to the right. The graph is shifted to the right by 1 unit. So the graph will shift 1 unit to the right. The graph will shift 1 unit to the right, and so that means we will add 1 to each x coordinate. To obtain this new graph, we'll add 1 to each x coordinate. All right. So we already plotted the graph of 3 power x. So we can also go back to that graph and plot 3 power x minus 1 on top of it. All right, so we already plotted the graph of 3 power x, and we know that when f of x is equal to 3 power x minus 1, the graph is shifted y units to the right. So instead of whenever x is -2, now x becomes -1. So the graph shift to the right by 1. So instead of um, x being -2, x now becomes -1. Instead of x being -1, here becomes 0. 0 becomes 1, 1 becomes 2, and 2 becomes 3. So this becomes the new x coordinates for x, 3 exponent x minus 1. All right, so the y coordinates still stay the same. So we can use these points to plot the graph now. So when x is -1, so when x is -1, y is 1 power 9, which is just about here. When x is 0, when x is 0, y is when x is 0, y is 1 power 3. So that will be about here. When x is 1, y is also 1. So that will be about here. And when x is 2, y is 3. And when x is 3, y is 9. Will be about here. So you can see that the graph so let's say f of x is equal to 3 power x minus 1. So we can see that the points, the x coordinates have shifted. The x coordinates have shifted by 1 point to the right. So compared to the original. So for example, this point here is 1, 1, and the original and the previous was x was 0 and y was 1. And the previous here is x is 0 and y is 1. So it's shifted by 1. This point, the original was -1 and 1/3, -1 and 1/3, whereas the new one is x -1 and 1/3. The new one is 0 and 1/3. So the x is shifted by y unit to the right, whereas uh, the um, whereas the y coordinates all stay the same. All right, so let's continue. All right, so now let's discuss the natural base E. The natural base E. Now let's discuss the natural base E. Okay, so uh, the number E, which is the natural exponent, uh, is defined as the value that 1 plus 1 divided by 1 plus 1 divided by n power n Um, the natural number, E is defined as the value of this series 1 plus 1 power n, 1 plus 1 divided by n exponent n. What this approaches as n approaches infinity. So the evaluation of this series as n approaches infinity, and that numeric value is approximately 2.7118281827. So let's the function f of x is equal to e power x is called the natural exponential function. It's called the natural exponential function. Okay, so let's look at an example on this. The exponential function f of x is equal to 1144 1144 1143 exponents 0.035325 x exponential function 1143 e power 0.0325x models the gray wolf population of the Western Great Lakes. Western Great Lakes, f of x, and x is in years. X in years after. X is the number of years after 1978. And now our question is, project the gray wolf wolf's population in the recovery area in 2014. All right, so we are given a function f of x which models the number of gray wolf population after 1978. So to find the population after any number of years after 1978, we will first have to find the number of years from 1978 to that particular time point in the future. So between 2014 and 1978, there is 36 years. That is 36 years. There is 36 years. There is 36 years. So f of 36 is equal to 11443 e power 0.0325 for 36. This is approximately, if we evaluate this, it will be approximately 3686 or 3686. So the wolf population in 2014 is projected to be 3,686 in 2014. All right. So now let's look at other uses of exponential function, which comes in using it in a compound interest. So we have formulas for compound interest. Okay, so formulas for compound interest. So after T years, after T years, after T years, the balance A after 2 years, the balance A in an account with principal P and annual interest rates. Interest rates are, and the interest rate, we always write it in decimal form, although it may be given as a percentage. We always write it in decimal form. Although it may be given as a percentage, we have to convert it to a decimal form. Is given by the following formulas. All right, so for n compounding periods, n compounding periods per year. For n compounding periods per year, the amount will be P times 1 plus R divided by N power N times T. And for continuous compounding, um, compounding, the amount will be equal to P times exponent ERC. So we have two formulas, continuous compounding and N compounding periods per year. All right, so let's use an example to go over some of this formula. So this would be our example 5. So it says the sum of $10,000 is invested at an annual rate of 1.08%. Find the balance in the account. Find the balance in the account after 5 years, subject to quarterly compounding. All right, so the amount after a number of years that is compounded n times a year at interest rate R, A is equal to P times 1 plus R divided by N power N times T. All right, so here our principal is 10,000. And so 10,000 times 1 plus our R is 1.08%. So we convert it to decimal. So 1.08 divided by 100 is 0.0108. And this divided by N is compounded quarterly. So every quarter of the year is compounded. So that means there are 4 quarters in a year. So that means every year is compounded 4 times. So N is 4. And so power N times T. So N is 4 and T is 5 after 5 years. So T is 5. All right, so if we evaluate this on our calculator, I will get approximately 10,554.08. So this will be the amount after 5 years at 1.08% interest rate. So if you invest $10,000 for 5 years and it's compounded quarterly at an annual rate of 1%, this is what you get after 5 years. All right, let's look at another example. So this should be our example 6. And it says a sum. So the same example 5, but now we are going to compound it continuously. So it says a sum of $10,000 is invested at it's invested at an annual rate of 1.08%. Find the balance find the balance find the balance in the account after 5 years, subject to continuous continuous compounding. So continuous compounding amounts is equal to P times exponents e power RT. So our P is 10,000. So 10,000 exponents. Our R is 1.08%. So in decimal, is 0.0108 and times T, which is 5. So if we evaluate this, we're going to get approximately 10,000, 554.85. So almost the same as what we had for compounding for 4 times in a year. All right, so let's look at another example here. This would be our example 7. Let's look at our example 7. Okay. So our example 7, it says, let's write the question down. So this would be our example 7. This is the function just a moment. This is the function n of t is equal to 40,000 divided by 1 plus 30 e power minus 1.5t describes the number of people, and t who became ill with a virus became ill with a virus 2 weeks. The virus 2 weeks after its initial outbreak. In the town with 40,000 inhabitants. The horizontal asymptote in the graph indicates that there is a limit to the epidemic's growth. Okay, so A, how many people became ill with the virus when the epidemic began. All right, so at the time that the epidemic began, um, the time is 0. So T will be 0. So NT represents the number of people who became ill after T weeks. So NT is equal to 40,000 divided by 1 plus 30 power e power minus 1.5 T. So that this is T weeks. So this is after T weeks. So at the time that the epidemic began, that is the 0 week. So T will be equal to 0. So this equals to 40,000 divided by 1 plus 30 power e power minus 1.5 times 0. So this will be equal to 40,000 divided by e power minus 1.5 times 0 is 0, so e power 0 is 1. So this will be equal to 40,000 divided by 31. And so if we divide this on our calculator, we should get 40,000 divided by 31. It should give us about 1,290. So about 1,200. So this is approximately 1,200. And let me write it well. This will be approximately 1,290.32. And since we are talking about human beings, we can round this up to 1,291. So this will be the number of people that became ill after when the epidemic began. That is at the 0 week. And B, it says how many people were ill by the end of the 4th week. So by the end of the 4th week, T is equal to 4. So we'll be finding N of 4, which is equal to 30,000, which is equal to 40,000, excuse me. Which is equal to 40,000 divided by 1 plus 30 power e power minus 1.5 times 4. And if we evaluate this on our calculator, this should be equal to 2. If we evaluate this on our calculator, this should be approximately 37,231.38. And so because we are talking about human beings, we can also approximate round this up to 37,232 people by the end of the 4th week. Okay, so this is our last example, and this brings us to the end of section 4.1, and I'll see you in section 4.2. Thank you. Bye-bye.